Okay, so let's dive in. We're going to tackle a problem that, on the surface, it seems almost trivial, right? We're taking a deep dive into the infamous three-body problem.
It really is the ultimate paradox of classical mechanics. I mean, you'd think three objects orbiting each other. How hard could it possibly be?
Especially when you consider that Isaac Newton totally nailed the two-body problem back in, what, 1687?
Exactly. With two bodies, say, the Earth and the Moon, Newton gives you this perfect, clean, analytic solution. You could write down an equation and just predict their paths forever.
But then you add just one more body.
And everything just, it breaks. The entire system descends into what we now know as chaos.
That third little bit of gravity makes the whole thing so complex that for most starting points, there's just no general closed-form solution. You can't write that one tidy equation anymore.
And that's really where classical predictability as a concept just dies.
So that's our mission today. We're going to explore this huge mathematical hurdle. We've got sources on everything from the birth of chaos theory to these really bizarre special orbits and even the AI that's trying to tame it all now.
And it's funny how it seeped into pop culture. I mean, when you see a show like Three-Body Problem and they visualize those three suns in those wild, erratic orbits,
Yeah.
that's it. That's the problem's chaos played out on a huge cosmic scale. It's the most visceral symptom of what we're talking about.
That sets the stage perfectly. So let's unpack the sheer size of the challenge here. Our sources say the Newtonian equations for this are equivalent to 18 first-order scalar differential equations. Now that sounds very technical.
It does, but what it really tells you is the complexity. Think of it like this. For each body, you have to track its position, x, y, z, and its velocity in those three directions.
So that's 6 variables for one body.
Right. 6 variables times 3 bodies. That's your 18. 18 independent numbers you have to know perfectly at the same instant. And any tiny error in just one of them, it just cascades.
And trying to solve this very problem is what led to, well, one of the biggest breakthroughs in the last century and a half. I'm talking about Henri Poincaré and the beginning of chaos theory.
Yeah, and he wasn't even looking for chaos. He was studying a simpler version of the problem, and he was trying to prove stability. But instead, in the late 19th century, he stumbled on this radical idea.
Sensitive dependence on initial conditions.
Exactly. He realized that the tiniest, most infinitesimal difference in where you start leads to just wildly different outcomes down the road.
He had that amazing quote about it, something like, "A small error in the former will produce an enormous error in the latter. Prediction becomes impossible."
And that's the butterfly effect. You know, decades before the term was even coined, it completely changed how we see the universe. It forced us to make this really sharp distinction between determinism and predictability.
Okay, so hold on. If the laws are, I mean, they're based on Newton's fixed rules, right? They're totally deterministic.
They are, yes.
So why can't we just, build a computer that's powerful enough to measure everything perfectly and just beat the chaos?
And that is the core conflict. The laws themselves are set in stone. The future is technically fixed by the past. But to actually predict it, you would need to define those 18 variables with absolute infinite precision.
Which you can't do. I mean, any real-world measurement has some error, no matter how small.
Exactly. And Poincaré's big insight was that in a chaotic system like this, that tiny, unavoidable error doesn't just stay small, it grows exponentially. It blossoms into what he called enormous uncertainties. So yeah, the physics is predetermined, but our ability to actually know that future it's fundamentally limited.
So the general problem is just a spiral into chaos. But, of course, mathematicians love finding little pockets of order in all that mess. So let's talk about the special solutions, the ones that do work.
Right, there were the historical ones for the 18th century. You had Euler's, where the three bodies are all in a straight line, and then Lagrange's, where they form a perfect equilateral triangle.
But the hunt for others went on for centuries. And then in the year 2000, we get this just astonishing breakthrough from Chinsener and Montgomery, the figure-8 orbit.
It's just a remarkable piece of work. So elegant.
Tell us about it. What makes this orbit so special?
Okay, so it only works for three
While
equal
there's
masses,
no
and they're
general
all moving in a single
solution,
plane. But the
scientists
really
have
key
found
thing is
what
that
are
it has
called
zero
special
angular
solutions
momentum.
or
And
periodic
why is
solutions.
zero angular momentum so important here?
Well, angular momentum is basically a measure of how much something is spinning as a whole system. If it's zero, it means the bodies are only moving relative to
It's
each
like
other, not
finding
rotating
a
around
few
some central
calm,
point. It allows them
predictable
to just
eddies
chase
in
chase
a
each other along
raging,
this
chaotic
fixed
river.
figure-8
One of
shaped
the
path.
first
Like a
sets of these
It is. It's like a
solutions
cosmic
was
ballet.
found
They
by the
trade places. They
mathematician
pass through these points
Leonhard
where one is
Euler.
exactly in the middle of the other two, but they never collide. It's a
Right.
perfect repeating loop.
And the way they proved it existed is just.
Yeah.
It's peak mathematical creativity. They use something called a variational method.
Yeah, that's the simple way to put it.
Yeah.
You can think of it as looking for the path of least resistance, or, more accurately, the path that requires the least amount of mathematical action, the most efficient route.
But the tricky part was proving that this most efficient path didn't involve a collision.
Right. So what they did, brilliantly, was they calculated the action for their perfect figure-8 path. Then they proved, mathematically, that any path that did involve a collision would, by definition, have to have a higher action. It would be less efficient.
So crashing is literally less efficient than performing this perfect dance.
It's proof by optimization. It's incredible. Now, it's probably just a mathematical curiosity. You're not likely to find one out in space, but just knowing it exists is amazing.
Okay, so that's the elegant figure-8. Let's shift to the other set of special solutions, the ones that are actually, hugely practical for us, the Lagrange points.
Yes, and these come from the restricted three-body problem. This is where we assume one of the bodies is so small its gravity is negligible, like a tiny spacecraft orbiting the sun and the Earth.
And these are the 5 points, L1 through L5, where all the gravitational forces just perfectly balance out.
Perfectly. The pull from the two big bodies and the centripetal force you need to stay in orbit all cancel out, so you can just hover there.
So let's break down where they are.
You've got L1, L2, and L3, which are on the straight line connected to the two big masses. Those are Euler's old solutions. But then you have L4 and L5. They form these two equilateral triangles, with one point 60 degrees ahead of the smaller mass in its orbit and 160 degrees behind.
And this is where stability really comes into play. Because those first 3 points, the ones in a line, they're not really stable, are they?
No, they're what we call saddle points, unstable. If a spacecraft at L1 or L2 drifts even a tiny bit, it'll start to accelerate away. You need constant little thruster burns to stay put. We call it station keeping.
But L4 and L5, those are the cosmic parking spots, the gravitational safe zones.
They absolutely are.
Yeah.
They're stable equilibria, as long as the mass difference between the two main bodies is big enough. And for things like the Sun-Earth system or Sun-Jupiter, it's more than big enough.
So what makes them stable? If you nudge something at L4, why doesn't it just fly off?
It's this beautiful interplay between gravity and the Coriolis effect, that force that comes from the system itself rotating. If you get pushed out of L4
However,
or L5,
mostly
those forces
stable
combine
isn't the
to
same as
gently nudge you
permanently
back towards
stable.
the stable point. You
When
don't
we
escape.
run
You just end up
long-term
orbiting the point
simulations of the
itself.
You end
solar
up in this
system,
wide, stable,
chaos
kind of kidney
still
bean-shaped
rears
orbit
its
around the
head.
Lagrange point.
These
And because they're
simulations
so
show
stable,
that
they
while the
naturally
major
collect stuff over
planets are
billions of
likely to
years.
remain in
Trojan
their orbits
asteroids.
for
Exactly.
billions of
The
years,
huge
we
clusters
can't
of
be
asteroids at Jupiter's L4 and
100%
L5
certain.
points.
There's
We've
a
even found them
tiny
for Earth.
but
It's where the universe puts
non-zero
things to keep them safe.
chance
And this has
that
massive
Mercury's
applications for
orbit,
us. I mean, think
for
about the Sun-Earth
example,
system
could
and what we
become
use L1 and
eccentric
L2
enough
for.
over
L1,
billions of
which sits
years
between
to
us and the
cross
sun,
paths with
is perfect
Venus,
for solar
or even be
observatories.
ejected from the
Satellites like
solar
SOHO are
system
there because they get a
entirely.
constant
The
uninterrupted
three-body
view of the sun.
problem tells us
They're
that
never in Earth's
absolute
shadow.
certainty
And
over
L2 is now
cosmic
probably the most
timescales
famous
is
Lagrange point of
impossible.
all
We
because
live in a
it's home to the
system
James
that
Webb
is
Space
predictable
Telescope.
in the short
Why
term,
L2
but fundamentally
specifically?
Well,
unpredictable in the
JWST is an
very,
infrared telescope,
very
which means it has to
long
be kept
term.
unbelievably
Now,
cold. We're
let's
talking
connect
minus
this back to the
233 degrees
sci-fi
Celsius.
Right, so
concept that
its
got
own
everyone
heat doesn't interfere with the
talking.
images.
The idea of
Precisely.
a
And
planet
L2
in a
is genius
system
because
with
from that
3
vantage point,
suns.
the sun, the
Could
Earth,
life
and the moon
arise
are
on
all
such a
clumped together
world?
in one small
Based
patch
on
of
what
the
we
sky.
know about
Which
the
makes shielding it
three-body
so much simpler.
problem,
So much
it
simpler.
would be an
You only need
incredibly
one giant sun
hostile
shield, that
environment.
5-layered one,
Without
to
a
block the heat and
stable,
light from all three sources
predictable
at once. It lets
orbit,
the telescope
the
just cool
planet's
down passively.
climate
It's
would
an
be
engineering
wildly
masterpiece
erratic.
made
It
possible by
might get
purely
flung
mathematical
incredibly
solutions.
So we
close
have
to
the
one of
general
its
chaos,
suns,
and we have these
leading
little
to
pockets of
stable
perfect
eras of
order.
scorching
But for
heat
the
that
vast
boils away
majority of
oceans.
systems out there, complex star systems, interacting asteroids, how do we actually solve them?
That's where modern computing is just essential. The main workhorse is still what we call numerical integration, You just brute force it.
Step by tiny step.
Yeah, you take the starting conditions, you apply Newton's laws for a tiny fraction of a second, you get a new position and velocity, and then you just repeat millions and millions of times.
And this gets even more insane when you're dealing with something like the relativistic three-body problem, right? Like 3 black holes merging.
Oh, then you're in a whole different universe.
Yeah.
You're not just using Newton anymore, you're dealing with Einstein's general relativity. And that introduces completely new dynamics.
Such as?
Gravitational waves.
Yeah.
When these massive objects orbit each other, they radiate energy away as ripples in space-time. That radiation acts like a drag on the system, changing its energy and momentum constantly. Simulating, that is. It's unbelievably complex.
But now there's something new on the horizon, a real paradigm shift. And that's artificial intelligence. Specifically, these things called physics-informed neural networks, or PNNs.
This is a huge leap. A traditional AI just looks at a bunch of data and tries to spot a pattern. It doesn't know any physics. But PNNs are different. They're built with the governing equations of mechanics, Newton's laws, baked right into their learning process.
So they're not just guessing a pattern, they're forced to find a solution that actually obeys the laws of physics.
Exactly. It acts as a constraint, a regularizer. It stops the network from learning physically impossible nonsense. And because of that, it learns way more efficiently. The research shows they blow past older machine learning methods.
That's
they're
pure
much
chaos
faster than the old brute force
territory.
method.
So much
And
faster.
probably
The
not a
sources call them a
great place to
time-efficient
call
open-form
home.
solver.
So, the
Compared to the
three-body
prohibitively
problem
high
isn't just a
computational
brain
cost of
teaser
grinding
for
through those tiny time
mathematicians.
steps,
It's
PNNs
a
can give you
fundamental
incredibly accurate
aspect of
results
our
in a
universe
fraction of the
that
time.
governs
That
the
really
dance
brings
of
the whole story
stars
full
and
circle,
planets.
from Newton's
It
impossible
reveals
puzzle
a cosmos
to
that
Poincaré
is both
discovering chaos,
beautifully
through the
ordered and
beautiful geometry of the
terrifyingly
figure eight and
chaotic.
Lagrange points,
It shows
all
us
the
that
way
while
to the
we
raw
can
power of
understand the
AI.
laws of
But there's
nature,
one last
we
twist.
can't always predict
The
their
biggest paradox of all.
consequences. There
We've
are
been saying there's
limits
no
to our
general
knowledge,
solution. But in
boundaries to our
1912,
ability to
a
see the
mathematician named
future.
Carl
This
Sundman actually
beautiful,
proved that an
frustrating
analytic solution
problem
does exist.
teaches
Wait,
us a
what?
dose of
It is
cosmic
solved.
humility.
On paper, yes.
We live in a
He proved
pocket
it
of
could be
relative
expressed as an
stability,
infinitely long
a
converging
calm
power
harbor
series.
in a
The
chaotic
problem
universe.
is,
And
the
while the
series converges
fiction
so
gives us a
unbelievably
thrilling
slowly
story
that
of
it is, and I
aliens
quote,
dealing with this
useless for
chaos,
practical purposes.
the real
What does
science
useless
shows
actually
us
look like
just
here?
how
Well, to
lucky
use
we
Sundman's
are to
series
have
to
the
make just one
predictable,
typical astronomical
life-giving
prediction,
orbit
you'd need to
we
sum at least
enjoy
10 to
around
the
our
power of 80
single,
million terms.
10 to the
reliable
80
star.
million. That's
The
not even a
universe
number.
is
It's a
more
concept.
It's
complex
completely
and less
unusable by any
predictable
computer
than
we
we
could ever
might
conceive of building.
think.
Wow.
And
So
that's
paradox
what
is
makes
the
studying it
perfect,
so
beautiful
endlessly
answer exists on paper,
fascinating.
but in reality,
Thanks
we
so
can't
much
use
for
it. The real
joining me
challenge
on
is
this
finding a
deep
solution that's
dive
both
into the science
accurate
of
and
the
actually
three-body
usable. It really
problem.
makes you
If you
wonder,
found this
what other
fascinating,
ancient,
hit that
unsolvable
like
problems are
button
out there
and
just waiting for us
subscribe
to
for
combine
more
that old
explorations
perfect
into
theory
the
with the sheer
biggest
speed of
questions in
AI to finally
science.
crack them?
Let
That's
me
definitely
know in
something
the
to chew on.
comments what other mind-bending topics you'd like me to cover next. See you in the next video.